Hey everyone, today we are going to be doing a full reimplementation of the original DDPM paper, or the diffusion paper, essentially. Now, in one of my previous videos, which I will link down below, and in one of the cards above, you will see me doing the entire derivation of where all of these fancy looking equations come from, because there's a lot of formulas that go into diffusion, and a lot of the times people just kind of throw them at you, so you don't really get a chance to see where's the derivation, where did all of that come from. So we took our time and actually did the derivation in that last video. Today we're just going to blindly use those formulas and do an implementation of our diffusion model. Now, to do diffusion, there is a couple of light prerequisites that I'd recommend. The first one is you're already comfortable with attention and transformers. I have a video for that. I'll also link that. And so go ahead and watch that if you don't know anything about transformers and the attention mechanism. We're going to be glossing over some of the kind of details there because I already assume you know them. And then, of course, we'll also have to implement a UNET here. If you already watched my earlier UNET video where we did UNET for semantic segmentation, then you're already 90% of the way there. There's just a couple of extra details when it comes to diffusion that we need to implement into that UNET. So let's just go ahead and do a recap of what was diffusion. In diffusion, the main idea is we have a noising and a denoising process. So you start with an image. In this case, it's an image, but it could also be audio or something else. You start with an image and you iteratively add noise to your picture. And that's easy. We can add noise to a picture, no problem. But the hard part is taking that noisy image and denoising it. So this is where we train a neural network to essentially denoise our image. And so that's the main idea behind diffusion. Now, to add noise to it, it's not just randomly adding whatever you want. We have to define something known as the noise scheduler. So we add Gaussian noise at every single step. In this case, we're adding big T steps worth of noise. In most state-of-the-art models, that'll be 1,000, so we'll have 1,000 steps of noise. And so we're going to add 1,000 steps of noise iteratively. And the mean, it's Gaussian noise, the mean of the noise will always be 0. But the variance of the noise depends on a scheduler that we set ahead of time. And of course, higher variance noise is more noise and lower variance noise is less noise. And the reason for this is we want to have some control over the variance. We want to add little bits of variance at the beginning, or little bits of noise in the beginning, but lots of noise in the end. And of course, we need these things so we can actually train the neural network to undo the noise. So that's all the stuff that we're going to be looking at. Now, what we did last time, again, I'm not going to be digging too much into the math today, but there's a couple things that we need to define. Number one, we need to define the variance. So we can see here the forward process variance beta t can be learned by reparameterization. That's fine. So beta t, or beta, is essentially our noise scheduler, and we decide how much variance of noise we want to add at every single time step t. So we'll see how we define that. But if you remember, in our implementation, when we actually train the model, sure, if we want to say, oh, let's add 25 steps worth of noise, sure, we could for loop. We could add one step at a time, but we're just adding a bunch of Gaussian distributions over and over again to the original image, which means we know what that final Gaussian distribution will look like. And so we rewrite the noising process using the alpha parameter. And this is essentially just a trick to make our noising process more computationally efficient, because instead of having a for loop adding noise 25 different times, we can just add 25 steps worth of noise in one go, right? So instead of having to do a for loop. And so we'll be using this alpha parameter, which will be 1 minus beta, and then we'll have this alpha hat parameter that's just going to be the cumulative product of our alpha. So alpha hat 10 would be the product of alpha 1, alpha 2, alpha 3, all the way up to alpha 10. And so these are the couple things that we're going to need to define ahead of time. After that, basically our entire formulation will be focusing on this figure right here, the main figure, the algorithm. So for training, all we're going to do is take an image, x0, and if we want to add t steps worth of noise to it, well, that depends on the alpha hat, and then of course, alpha hat is here as well. So this is one core part of the equation that we're going to need to take some data x0 and add t steps worth of noise based on our beta scheduler. So there we go. So we're going to have to implement that. And then for the unnoising or the denoising portion, this is our formula right here, where we have, again, alpha, no problem. We're going to be computing that. We have an alpha here. We have this here is the estimated noise from our neural network. So our neural network predicts how much noise was here, and then we essentially remove that noise from our data. So that's the denoising process. So we have everything we need here. We also have the sigma t term here, and the sigma t term is just our variance of the denoising. So we can actually go up here. I wish it was all in one place, but that's okay. The sigma t is the same as this beta tilde t that you see right here, and that has the equation of this. So again, if you're unsure about what all these equations are, we derive every single step of where all of this stuff came from in that video. So if you go and watch that video, then it'll be clear exactly what we're looking at. The original DDPM paper, I feel like maybe didn't organize some of this stuff in the best way, so you have to hop around a little bit, but we have everything we need. So let's go ahead and just start implementing blindly these formulas. So what we are going to do, so this is kind of some of that derivation we did last time. That. So, okay, good. Yeah, we are good to go. Okay, so we're going to define our sampler. So the sampler has two things that it's going to need to do. So let's first do init. Self will have our num steps. This is going to be, by default, 1,000 steps is 1,000 steps worth of noise that we train with. So this will be big T is 1,000, so we can add 1,000 steps worth of noise. And then we have to define our scheduler for the variance. And this is completely up to you. There's a bunch of different schedulers that you can pick from. There's linear, which is what we'll be doing today, but there's also a cosine scheduler and stuff like that. And basically, it'll look like this. So we'll have a beta start. Let's just use some of the defaults that you'll typically see online. We're going to say beta start is 0.0001, beta end is 0.02, and then we'll do self.num steps is num steps, self.beta start is our beta start, and self.beta end is our beta end. So what we're going to do is define a sampler. We're going to call it def linear beta schedule. And it's just going to take this, and we're just going to return torch.linspace, and we're going to start at self.beta start. We're going to end at self.beta end, and we're going to have self.num training steps between the beta start and the beta end. So let's go ahead and take a look at what that looks like. So our sampler is going to be this. And we'll then have our self.beta schedule is going to be our self.linear beta schedule, right? So if we look at our self.beta schedule, you will see that looks like we have a bug, num training steps, because this should just be num steps, not training steps, my bad. You'll see that we have all of these numbers here, which at the very first number will be 1e to the minus 4, which is this, right? 0.0001 is 1e to the minus 4. And on the last step, we'll have 2e to the negative 2, which is just 0.02. So what we're saying is in the first step, we're going to add noise to our data that has mean of 0 and variance of 0.0001. And then in the next step, we're going to add noise to our image that has 0 mean and 0.00011992 variance worth of noise. So you can see that the amount of variance we're adding, basically the amount of noise we're adding, because the larger variance means larger amounts of noise, the variance is slowly increasing. So more and more steps means we're adding more and more and more noise to our image. And that's the main idea. So that's our variance scheduler, is just defining how much variance we add at every step, how much variance worth of noise we add at every step. So that's our beta scheduler. Oh, my bad. And so now that we have our beta schedule, of course the beta schedule is useful, but we actually don't use the beta schedule because this would require, if we want to add, let's say, 10 steps worth of noise, then we'd have to add this much noise, and then this much noise, and this much noise, and this much noise, ... We'd have to do every step individually and just for loop through them, which would still give you exactly the same result, but obviously is a little bit inefficient. And so in that derivation, we saw that using the kind of this other method, using self.alpha, is going to be 1 minus self.beta schedule. So this is just 1 minus beta schedule. Again, this is going into this part here. Our alpha is our 1 minus beta, and then our alpha hat, which is the cumulative product of our alphas. So alpha 1 is just alpha 1. Alpha 1 hat is just alpha 1. Alpha 2 hat, it'll be alpha 1 times alpha 2. Alpha 3 hat will be alpha 1 times alpha 2 times alpha 3, dot, dot, dot. So you get the idea. So it's just a simple cumulative product. So we can do self.alpha cumulative product is going to be torch.cumulative product of our self.alpha. And let's do it along the last dimension. There's only one dimension here anyway. And so we are good to go. This is essentially our setup for our noising process. All the parameters that we need. We have our betas, we have our alphas, and we have that cumulative alpha. Now that we have all of that, let's go ahead and write two methods. The first one's going to be def add noise. When we add noise, we're going to have to give it the image, right? The input, let's call it the image that we want to add noise to. And then we will have how many time steps worth of noise do we want to add to it. So that'll be time steps. And the way we'll pass this into our sampler will look kind of like this. So let's create some dummy data. We're going to do rand is equal to torch.randend. So we're working with images, so we know it'll be in the shape of batch size, by number of channels, by height, by width, right? So let's just say that's what it is. And then our time steps is just a index of, for each one of these samples in the batch, how many time steps worth of noise do you want to add to that sample? So we have 4 samples in the batch, so we need 4 time steps as well. So we can do rand time is going to be torch.randint. We know that we can add between 0 and 1,000 time steps because there's 1,000 steps set to default, right, in our sampler. So we can add up to 1,000 time steps. And then we will say that we want the shape to be, in this case, just 4, right? Print rand time. And so what you're going to see here is on the first image in the batch, we're going to add 498 time steps worth of noise. In the second image in the batch, we're going to add 148 time steps worth of noise, dot, dot, dot. And so that sets us up. And so all we need to do now is just quickly do a sampler.add noise. And this is the data we want to add our noise to. And this is how many time steps worth of noise we want to add noise for. Good. So now that we have that, let's go ahead and just implement it. So our batch size, let's go ahead and just store our variable dimensions, batch size by height, by width. It's going to be image.shape. So we're good to go there. And then we'll have a device is inputs.device. We're doing this because, of course, when we actually do this stuff, it'll be on the GPU. So, and this stuff we defined here is not necessarily on the GPU, so we just need to manage that. So we'll see why we have that in a bit. And so step 1, let's just quickly remind ourselves, what is the formula for the forward process? All we need to do is take our original data, multiply it by the square root of alpha hat t, and then we're going to do plus some noise term. This is us. We'll generate some noise, some standard Gaussian noise, 0, 1, mean 0, variance 1, and we'll multiply it by this term. So we can see we need the alpha hat term first in both cases. So let's go ahead and grab that. Our alpha cumulative prod time steps is going to be self.alpha cumulative prod, and we're just going to index it for the time steps, right? So what we're going to do is just grab from here the amount of noise, basically our alpha cumulative prod, alpha hat, for the different time steps. And if we take a look at that, print alpha cumulative prod time steps, you'll see we have something is missing. This should be image, not inputs. So let's go ahead and fix that. And, oh, my bad. There. So we can see that we indexed, and if we print time steps, the 431st time step has, this is the cumulative product of all the alphas for 431. This is the cumulative product of all the alphas for the 451st step. This is the cumulative product of the 701st step, dot, dot, dot. So you can see this is essentially our cumulative product happening, right? Nothing too concerning. That's everything we need. And that's the alpha hat that we're looking for. It's just we're doing it in batches. So we're, essentially we're indexing all 4 time steps at one go from our vector of alpha cumulative products. Now that we have that, we just need to make sure it's on the GPU, right? Because this will be interacting with the image, which could be on the GPU, so we want to make sure it's all in the same place. Now that we have all of that stuff, let's go back. So what we need to do is take our original image, multiply it by the square root of this thing, and then we need to multiply and add to it some noise multiplied by the scaling factor here. So let's just do it one piece at a time. So the first term is called the mean coefficient. This is going to be the alpha cumulative prod time steps, and we'll do it to the square root, right? So to the power 0.5. And then our variance coefficient is equal to the alpha, or it's going to be 1 minus alpha cumulative prod time steps, again, square root 0.5. So that clears out these terms. We have 1 minus this thing, square root of it. We have the square root of this. And now we just need to multiply it to x0, multiply it to some noise that we haven't created yet, and we will be good to go. So let's create some noise. Our noise is going to be torch.rand n, because we want Gaussian noise. And this will be 0 mean, variance of 1. And we're going to make sure the noise is in the same shape as our image, right? Same shape as our image. And now we actually have a little bit of a problem, and this has to do with broadcasting, so we can take a look now. Print noise, or let's just look at image.shape, which we know what it is. And let's print out our mean coef.shape. And you'll see that our image is in the shape of 4 by 3 by 64 by 64, but our mean, and of course the variance as well, is just 4. So these two tensors cannot interact with each other just yet because they're not the same dimension, right? We need some extra dummy dimensions in this tensor so we can broadcast the operation over. Okay, so how do we do that? All we need to do is just add some extra dimensions, and there's a bunch of ways we can do this. We can either do, we could do a dot unsqueeze -1, and then just repeat this a couple times, right? We can just do that. And now we have a 4 by 3 dummy dimensions, 1 by 1 by 1. And when we do some operation, multiply these two things together, then it's okay. We have these dummy dimensions, and it can broadcast on its own. Now, this seems like a little bit of a unclean method of actually implementing it. So let's just write a quick method that'll do this for you. So we can call this repeated unsqueeze. And what this is going to do is take some target, right? And it's going to take some input. Let's say our image, and it's going to, or let's see, let's call this tensor, right? It's going to take some target, it's going to take some tensor, and it's going to reshape the tensor, or just keep adding dimensions, dummy dimensions to the tensor until we meet the target shape. So we're going to do while target.dim, which is going to give how many dimensions are in this target. In this case, our target has 4 dimensions in it. But our tensor, in this case, the mean coefficient or the variance coefficient, only has 1 dimension in it, right? So we're going to keep adding dimensions to it over and over again. So while target dim greater than our tensor.dim, so if it's less, then we're going to do our tensor is equal to tensor.unsqueeze, there we go, -1. And we can return the tensor. So this is doing exactly what we had done before. It's just going to keep repeatedly unsqueezing this tensor over and over again, adding a dummy dimension until they're the same number of dimensions. So nothing too fancy. We can go ahead and add that in. Our mean coefficient is just going to be the self.repeated unsqueeze of the mean coefficient. And then similarly, our variance coefficient is going to be self.repeated unsqueeze variance coefficient, just like that. Looks like we have one mistake. So because we're passing that in, we also need to give it the target, and the target will be whatever the image shape is. So it's going to be image, just like that. Nice. So now if we look at our mean coefficient.shape and our image.shape, you will see that we have this and this. So this has added those extra dimensions on so we can do our operations, and PyTorch is happy because we have all the dimensions we need. So now let's just follow the formula. All we need to do is take our original image, multiply by this term, and then take the noise that we generated and multiply by this term and add them together. So let's go ahead and do that. That's just going to be our noisy image is going to be equal to the mean coefficient that we just generated times our original image plus our The second term will be the variance coefficient that we did above, and that's going to be times our noise, just like that. And that gives us our final return our noisy image as well as the noise, because we added this noise to our image. This is the noise we essentially scaled, so that's what we did. So we want to return both things back. What's the image, the noisy image, and the noise we added. And our neural network's goal is to predict the noise that we added to it so we can undo it as well. And so we should be good to go now. All right. Good. So that's our final output. Nothing too crazy. We have everything we need to do our next step. So this is the noising portion of our training. So this is, if we go back, this is us adding noise to our image. Notice there's nothing fancy, right? Nothing, we literally just follow the formula, nothing too crazy. And we just use the alphas to make the computation much simpler, because notice there's no for loop here through the time steps. It's just a single forward pass to add all of our steps worth of noise in one go. Good. So now we need to do a def remove noise. And so to remove noise, we have a image, right? So this is the image that has some noise in it right now. We'll have some time steps, right? So when we remove noise, the question is, okay, I have an image with these many time steps worth of noise. And my neural network predicted, so predicted noise, predicted that this is the amount of noise that was added at this time step. So go ahead and denoise it by one step. And so to do this, there's actually two steps that we're going to need to do. But let's remind ourselves, it's basically this formula. So we need to compute this chunk right here, and then we need to compute the sigma t as well. And so for all of this, we're going to need alphas. So we have our alpha t here, we need our alpha hat, we need our alpha. But also notice there's a 1 minus alpha here. So we could do 1 minus alpha, but we know that 1 minus alpha, as according to our formulation, if alpha is 1 minus beta, then beta is also 1 minus alpha. So we can rewrite this 1 minus alpha t term in the numerator as just beta. They're the same thing. So let's go ahead and start that. So the first step we're going to do, just like before, batch by channels, by height, by width, is going to be input.shape, or not input, but image. I'm saying image right now because we're working on images, but this scheduler would work almost identically for any kind of data, videos, audio, you name it. And we'll have devices, our image.device. And there's one other small caveat, and we'll take a look at what that is in just a second. But we need to actually create a mask for if the time step is 0. So if our time step is 0, what does that mean? That means alpha t is fine and alpha t is fine. For the most part, everything seems fine, except in our sigma calculation. What does that mean? Let's go up. Our formula for sigma was this beta hat over here. Notice that for some t, we reach back to a t minus 1, which is fine for all t's up to 1. But if we have t as 0, then t minus 1 becomes negative 1. So it becomes alpha hat of negative 1, which doesn't make any sense. So we're going to have to do something called a empty product. It's just a simple rule that we'll have to handle that exception for. So we'll do that in just a second. So let's just create that mask equal to 0 mask. And this is going to be time steps is 0. So this is just a mask telling us, is one of the time steps 0? If it is 0, then we just have to do a small condition check. But we'll get there in a second. So step 1, we need our alphas and our betas. So let's do beta t. It's going to be self.beta scheduler schedule, and it's going to be at that time steps, right? Whatever the time steps are. .to device. Make sure it's on the GPU. Similarly, we'll have our alpha t, again self.alpha time steps. And then again, it will be .to device. Next, we need our two cumulative products. So first one is going to be alpha cumulative prod t, right? So it's going to be the cumulative product. It's going to be self.alpha cumulative prod time steps .to device. So that gives us everything we need. We have our alpha hat t. We have our beta t, right? So that's the 1 minus alpha t is just beta t. And we have our just alpha t. So we have alpha t, alpha hat t, and beta t. But we also need, according to the formulation, is alpha hat t minus 1, the previous time step. That's no problem. We can go ahead and grab that. We can do alpha cumulative prod t prev for the previous time step will again be self.alpha cumulative prod. So it's still going to be the same cumulative product, but instead of just time step, it's now going to be time steps minus 1, right, for the previous time step. And this is where the problem arises, because if our time steps was 0, then we're indexing this for -1, which would actually be the end of the list, which doesn't make any sense anyway. But more importantly, we're indexing a time step that doesn't exist. So this is the condition that we just need to verify with this up here. And so this is called a empty product. I can quickly show this. This is basically one of the math rules that you just need to know, like e to the power 0 is 1. Why is it? Because it's just mathematically convenient. In the same way, this is a product, right? So we're doing a cumulative product here. But you can see if Pm is the product from 1 to m, so P3 is A1 times A2 times A3, and that's it. Well, P0 would be I from 1 to 0, which is going like backwards in product, and that doesn't make any sense. And so this is a product with no factors at all, evaluates to 1. It's just one of those kind of numerical rules that we have for a lot of different math formulations. Again, like y is e to the power 0, 1, it's kind of like one of those things. So we just need to handle that exception. All we're going to do is our alpha, remember these are cumulative products, if our time step, so equal to 0 mask, if the alpha we grabbed is, in this case it would have been -1 because we did 0 minus 1 here. We're just going to do a quick check for if the time step was 0. If the time step was 0, then this number would be correct for those indexes. So we're just going to go ahead and set these to 1, right? Go ahead and set them to 1, and they are now correct, right? This is kind of our check for the empty product. Good. So that handles everything. And now it's really as simple as just following the formula again. So just like before, we need to make some noise. Torch.rand and like input, or not input, image. What is this noise? This noise will be this term right here. We have z right here, so that's the noise term we just generated. So let's go ahead and compute our, let's do this term first, sigma t. So of course we'll be doing sigma squared t, and then we'll actually take the square root of it to get sigma t. So let's do the variance first, and then we'll compute sigma from there. So step 1, let's compute that term. So our variance is equal to, and now let's just following the formula. We knew it was beta t times, and let's just remind ourselves again, just so we're looking at it as we're going. It's going to be our, where is it? Here we go. It's going to be beta t times 1 minus alpha hat t minus 1 divided by 1 minus alpha hat t. So that's our formula. So it's going to be beta t times 1 minus our cumulative prod for the previous time step, so alpha cumulative prod t prev, divided by 1 minus alpha cumulative prod t. And there we go. That's our variance term. Now, of course, we don't really want the variance. We want the standard deviation. So we can just go ahead and compute this entire term. It's going to be our variance term that we just computed right here. We'll take the square root of it and multiply it by the noise. Now, just like before, this variance term is just a number with the wrong number of dimensions. So we need to again do a repeated unsqueeze, just like we did here. Do the repeated unsqueeze to make sure the variance term is in the same dimension, has the same number of dimensions as the noise term. So let's go ahead and do that. We're now going to do a quick variance is equal to self dot repeated unsqueeze, and we're going to do it to the image and our variance. Just go ahead and add dimensions. Once that's done, we can do, let's call this sigma tz. It's going to be our variance. Take the square root, so it's the standard deviation, and multiply it by our noise. And that knocks out this first formula. We took the square root of the variance, giving us sigma t, multiplied it by noise, and we're done. Now let's do the rest of it. And then we can add them all together at the end. So that was the first part. The second part is now going to be our noise coefficient is going to be, let's call it that, it's going to be beta t divided by 1 minus alpha cumulative prod t to the power 0.5. Where did this come from? Let's just quickly look again. This is going to be our, up here, it's going to be this entire term that we just multiplied by. So it's going to be this beta t, remember it's 1 minus alpha t, which is beta t. So it's beta t divided by square root of 1 minus alpha hat t. So that's this term right here. Beta t divided by 1 minus alpha, spell that right, alpha cumulative prod t with the square root around it. So that's the first term. Then we will have, again, just like before, we're going to have to do this repeated unsqueeze to add those extra dimensions. This time it will be on the noise coefficient. So there we go. We have our noise coefficient. And next step is we need our 1 over square root alpha t. So that's easy enough. Let's go ahead and do that. This is going to be the reciprocal root alpha t is going to be the alpha t to the power negative 0.5, right? So that's, again, we're taking the reciprocal square root of alpha t, so that knocks out this term right here. And so all we need to do is just take our noisy image, xt, subtract it from multiplying this coefficient to our predicted noise, subtract it, multiply it, add this term, and we are done. So we can go ahead and do that. Again, in the exact same way, we just need to make sure we add the extra dimensions here. So let's just throw that in here. There we go. And so we can now wrap it up. Our mean is going to be the denoised. There we go. Mean is going to be denoised. Denoised. Actually, no, sorry. It's going to be the reciprocal root a t. There we go. So it's going to be this term times our input, so image, minus our noise coefficient, right? So image minus noise coefficient times the predicted noise. And we can throw an extra parenthesis around here. So that knocks out this term. We had a reciprocal root times our image, our noisy image, minus the noise coefficient times our predicted noise. So that's all of this stuff. Reciprocal root times our image minus the noise coefficient times the predicted noise. And our final denoised image is just going to be the mean that we computed here plus the sigma tz, because all we had to do was take this stuff here, add this on, and we are golden. And so now we can return our denoised image, just like that. So to test this, let's do our pred noise is equal to torch.randan, again 4 by 3 by 64 by 64, because we predicted what the noise would be at all the different pixels. And we can now do sampler.remove noise, and we're going to give it the image, our time steps, and the predicted noise. So rand time, and our pred noise. Let's see if this works. And there we go. So that is our denoised image. And so this is a pretty standard scheduler for the DDPM implementation. This should work for basically everything. I use it all the time. So there we go. We have everything we need in here to train our model. Now that we have that, let's go ahead and start defining the rest of the model. So this is again going to be a standard UNET. So it'll be like the UNET implementation that we did in the UNET video, but there's a couple of extra things that we need to add in. The first one is you're typically going to have some type of a attention mechanism inside the model. So let's go ahead and incorporate that. And then once we have that, we can then start adding in everything else. So let's go ahead and add in an attention mechanism. This is, again, going to be standard transformer block. So it's going to be class, self, attention, and then dot module, def init self, and we're going to have how many channels go into the self attention. We're going to have num heads. Let's just do 12. It's fine. Attention p is going to be 0, basically our dropout for the attention. We'll then have our proj p. This is going to again be 0, so that's our dropout for the projection layer, and that should be good. So just like always, we're going to have a super.init, and we will then do self.numHeads is numHeads, self.headDim is headDim, or this is going to be our in channels divided by numHeads. You'll see what that looks like in a bit. Self.scale is going to be self.headDim power negative 0.5, right? Because you divide by the square root of the embedding dimension. And then we're going to have our standard setup. So self.qkv is going to be a nn.linear layer, and it's going to go from in channels to in channels times 3. And we'll follow the shapes. Then we will have a quick self.attention p is going to be attention p. And then we'll have our self.projection layer is nn.linear in channels to in channels. And then finally we'll have a self.projection dropout, or dropout layer, nn.dropout, again, projection p. So this is going to be slightly different from the standard attention implementation because we're working on images. So we're going to see what that looks like in just a second. But for now, let's just go ahead and get started. So self x. So the way this is going to work, and let's go ahead and take a look at it now. Rand is equal to torch.randn. And let's say we have a batch size of 4, and then we have, let's say 64 channels, and then we have a 14 by 14 image, right? So let's say that's our image, or some output of some convolution. So what we end up doing is we reshape it. We say that we're going to do rand.reshape, or actually, first of all, let's do rand.permute. So the batch size still stays at the beginning, but then we're going to move these two dimensions to earlier. So we can actually, and actually it might be easier just to do it this way. We can do flatten after dimension 2. Oh, that doesn't help. Let's look at the shape. There. So we have 4 by 64, and we flatten the 14 by 14 because this is basically a 14 by 14 grid of values. And so I'm saying there's 196 values in there, and each value has 64 channels. And so then we can reshape it dot transpose -1, -2. And so then the 196 and the 64. This should actually feel pretty familiar because we did this in the vision transformer, a very similar operation in the patch embedding module, where we went from the patch embeddings to the basically the way we set it up for the transformer. This is exactly the same thing. So all we did is just take the spatial dimension, move it here, and each spatial dimension is defined by these 64 numbers, right? So this is kind of like the embedding dimension, but actually it's our channel dimension, but same thing. So we'll be doing that manipulation a little bit later, but I'm assuming that the image is coming in to our self-attention module in the standard attention shape. So this is going to be some batch size by sequence len by embed dim x dot shape. So some standard shape. Let's call this rand is there. So we've gone ahead and reshaped it. Let's call this attention is equal to self attention, and our input channels in this case is going to be 64, right? The embedding dim that we're working with, our in channels, is going to be 64. So 64. And let's do our num heads. Oops, sorry, don't need that just yet. Our number of heads, let's do num heads, is going to be, let's say 8, because 64 is evenly divisible by 8. So we are happy. Looks like I spelt something wrong here. Self. Here we go. Self. There we go. All right. So now that we have that, let's go ahead and define the forward module. And this is just like always, we'll have a QKV. So I'm doing the entire QKV. I could have also had 3 different, okay, let's just do it the standard way. So we'll have self.q is nn.linear with in channels to in channels. And we're gonna have 3 of these, right? So we're queries, keys, and values. Q or query, key, value, right? These are our 3 projection matrices. And now that we have that, we can do our Q is self.query x, K is self.query y, or no, x, and V is self.query x, or self.query, and then we're going to do key and value. There we go. All right, so now that we have our QKV, we do our standard operation, but we do need to set this up a little bit. So to do this, if we do print q.shape, and we look at, if we pass into our attention our random data, we're going to see that we have this, right? That's what passes in. But now we need to go ahead and split the 64 up by the embedding dimension. So we can do dot reshape, and we're going to leave the batch size and the sequence length alone. But the embedding dim 64 is going to get split in, and let's do number of heads as 4 instead, just so we have different numbers. We're going to have self dot our num heads by self dot head dim, right? So we've gone ahead, taken the 8, split it into 4 and 16, and then we can just do our final dot permute. It's going to be the batch size by, we're going to move the number of heads to earlier, move it earlier so we can parallelize over it, and then we're left with 196 and 16. So really we just need to permute these 2 dimensions. We don't even need to do anything else. So dot transpose 0, 1, 2. And we'll end up with this. So that's our data. That's essentially our reshaped data. And that's actually all we need to do. Again, if you're unsure about any of these details, because I'm going through them kind of fast, go ahead and watch my in-depth transformer video where we see why and where all of this comes from. So we're going to do that to our QKV. Now we could write the attention formula out doing QK transpose and all that sort of stuff, but because this is supposed to be a little bit quicker, we're just going to use our standard scaled basically flash attention, right? So built-in flash attention, scaled dot product attention, and this is going to take Q, K, V, and we'll have dropout P is self dot attention P, just like that. And so that's going to go ahead and compute attention on our queries, keys, and values for us. Or we could have actually, we could have done all of this, and that would give us exactly the same results. But why not just use the faster implementation when we can? Now that we have that, we can check print x.shape. We will see that we have our data in this shape. We just need to put it back the way we found it. So let's go ahead and do that. X is going to be x dot, again, transpose, flip those 2 dimensions back around, and then just reshape it back to batch size by sequence length by embed dim, just like that. And finally, we need to send this through our projection layer, self.proj, because we did multi-head attention. We want all the heads to get to know each other, so that's how we do this. X is then again equal to self.proj drop x, and we return x. And we are done. Standard attention mechanism, nothing too crazy. Now that we have that, now that we have attention, let's go ahead and implement a standard, multi-layer perceptron, right? So this is just a stack of 2 linear layers. You could do it however you want. Class MLP, nn.module, def init, self, and then it's going to be basically, again, in channels, which is our embed dim, the MLP ratio, which is 4 standard, and then our MLP dropout is going to be just 0, let's just say. And so we'll have super.init, and we can finally just go ahead and do the rest of it. So very quickly, self.fc1 is a linear layer that's going to go from in channels to in channels times the MLP ratio. And then we'll have a self.activation function. It's going to be We should probably be using a different activation function here because it seems like CLU and some of the other stuff works better for diffusion, but let's just go with GLU for now, it's fine. We're not building a state-of-the-art model in this iteration. Next time we're going to actually build a full state-of-the-art diffusion model that'll be closer to some of the models you see online, so we'll see that later. Either way, we have some activation function here, GLU, and then we're going to have some dropout, dropout, MLP, and then we're going to have a second activation. I guess we don't need to really define it again, so that's fine. Then we're going to self.fc2 is nn.linear. It's going to go from in channels times MLP ratio, just like we had there, back down to just in channels. And finally, we're going to have self.drop2 is nn.dropout MLP, just like that. So standard, just a stack of some linear layers. Self x, and this is just going to be x is self.fc1 x is self dot the activation function x is equal to self dot dropout x, right? So we need our drop one, so drop 1x, and then again just repeat x is equal to self dot fc2 x is equal to self dot drop to x, and we can return x. So all we did is take our data, pass it through a linear layer, an activation function, a dropout, another linear layer, another dropout, and we're done. So standard attention. And so then we can go ahead and create a transformer block, and it's just gonna wrap these two things we wrote earlier together. So I'm gonna go ahead and just copy the init here. So just so I don't have to type it all out, there's nothing fancy in here, it's just everything we had from earlier. We don't have user attention, we're doing that by default, so that's fine. So how many heads, MLP ratio, your those, we don't need U anymore. And we're going to be using a default there as well, so we can keep it simple. So that's just all the stuff we had from earlier, and we have our normalization. This is going to be nn.layer norm. Again, one more nn.layer norm. And this is our standard transformer block, right? So again, if we look at our attention is all you need paper, just as a super quick recap to anyone that doesn't remember, we have our attention block, we have our feed forward, and then we do an add a norm, add a norm. The norms are going to be layer norm, and the adding is our residual connection. So that's what we have left to implement. So let's go ahead and just put that all together. So it's going to be def forward self x. And so now here's the key part. Our input data x is an image. So it's going to be batch size by channels by height by width. That's the data coming in. But of course, attention, I just assumed everything was in the kind of the sequence shape. So let's just go ahead and do that reshape that we just talked about earlier, what we have right here, essentially, right? So x is going to be equal to x.reshape. First, we're going to do batch size. We could also do flatten, but I just want it to be clear. By channels, by height times width, right? So we're going to flatten those two dimensions, and then dot permute. We want the batch size to stay the first dimension, the height times width to be the sequence dimension, and then channels to be the embedding dimension. So it's going to be 0, 2, 1. 0, 2, 1. And then that's, now that we have our data, all we need to, in the correct shape, we just do standard attention. X equals x plus self.attention, self.norm 1x. So go ahead and take x, normalize it, pass it through attention, and then add it to x. That's a residual connection. Again, x is equal to x plus self.the multi-layer perceptron. Again, self.norm to x, just like that. And so that's, again, we add in norm. And finally, now that we have our data ready to go, it's gone through attention, we just want to put x back into the original image shape rather than this shape. That's pretty straightforward. We can do x is equal to x.permute 0, 2, 1. Just put it back because we flipped 1 and 2 and 1 here. So doing 0, 2, 1 again, we'll just put it back exactly how we found it. And then that will give us our image, but that's again going to be in the shape of batch size by channels by height times width. We want to take the height times width and just unshape, basically reshape it to height by width. So we just want to split this dimension up. So let's go ahead and do that. Dot reshape. Reshape. I'm just going to go back to batch size by channels, by height, by width, just like that. And we can then return x. So attention here is being computed along the spatial dimension of our image, just like a vision transformer, right? You're computing how every kind of patch of the image is related to every other patch of the image. So it's along the spatial dimension is where it's happening. Good. So that gives us our setup. We can go ahead and try it out. Let's do our, let's call it T for transformer block. Our image can just be the regular image shape, just like here. And then we have an embedding of 64 and number of heads is that. So let's just go ahead and pass this in and see what happens. Okay, looks like there's a bug. Fused attention is not defined because we are using the default. And then here we're also using a default, so we don't need to define them ahead of time. Again, I misspelled somewhere, so drop self. Okay, and there we go. We're good to go. Dot shape. The input shape and output shape should be same. It's just we had a attention computation along the spatial dimension, and there we go. That's exactly right. And so we've now completed the transformer, right? The attention mechanism, essentially. So that was the next step. All right, up next, our sinusoidal time embedding. So this is another key part of the diffusion model, and that when we're adding, let's say 1 step, 2 steps, 3 steps, like how many steps of noise we're adding to our image or to our data, it's a good idea to tell the model how many steps of noise we're adding. And so to do that, we're just using positional embeddings, just like the standard, the traditional transformer positional embeddings, the sine cosine embeddings. So we're just doing position embeddings here, and all we're going to do is inject this positional information into our UNET. So we tell the UNET, hey, this is the image you're looking at. This image has been noised 800 times. And the positional embeddings will tell it that information of how many times of noise has this image gone through. And so this is just lets the model keep track of the number of time steps worth of noise. That's the important part. So let's go ahead and do that. So we can do a class sinusoidal time embeddings, and then dot module def init. And all we need to let it know is the time embed dim. So what is the embedding dimension that we want to use to represent every single time step? And our scaled time embed dim. And what we're implementing here is literally these formulas directly from the attention is all you need paper again. So nothing crazy. To do this, you can see it's like we have a position, which we'll do later, divided by 10,000 to the power 2i over d model. Okay, and then cosines will be every odd position. So 2i plus 1 over d model. And so that's basically what we're going to do. Now, what you can see here is basically in our, let's see, what's the best way to show this? Let's say we have 1,000 time steps, because that's what we have, and we're using an embedding dim of 512. So we're representing every position in time with 512 numbers. In the standard implementation, you'll have every even index along the embedding dim be a sine, and every odd one be a cosine. But I'm just going to do like the first half of them as sine and the second half of them as cosine, because I don't think it actually matters where they are in the end, as long as we have both sine and cosine information along that embedding dimension. So that's what we're going to do. We're just going to inject that information into here. So we just need to follow this. So we're going to create a placeholder where position is 1, and then we can scale it up by multiplying. So what we need is all this other stuff on the inside. So let's go ahead and do that. This is going to be, let's go ahead and delete you. All right, so it's going to be super.init, just like always. And we're going to do self.inverse frequencies, right? That's what they are. They're just frequencies that we'll be doing our sine on. It's going to be nn.parameter, just to make sure it's something that can move to the GPU. And we're just going to use a placeholder of 1 divided by 10 1000 to the power, and now it's going to be torch.arange, torch.arange, one more parenthesis, torch.arange, from 0 to time embed dim, right? So however, whatever, so in our case it was 512, but whatever is the embedding dim you want to use to represent the time. But we want to do it in every other one, right? Because it goes 0, 2, 4, 6, 8, so, you know, in chunks of 2. So we're going to do every other one, just like that. And we want to make sure this is a float. So we're going to do a, this was just a sanity check, otherwise the data type doesn't work out. So make sure this is all floating point, because arange will produce integers. And then we're going to do this and divide it by our D model, right? So D model, so let's go ahead and do that. That's just going to be our time embed dim, just like that. So we can do our time embed dim, just like that. So that's our D model. And we want to make sure these parameters here should not be trainable. Let's add that last parenthesis. Are we missing one? No, it should not be trainable. So we're going to do a quick requires grad equals false, just like that. And so that is basically the inside of that thing. And so to actually access our data, to access the time step, we can do it this way. We can do def forward self, and we're going to be providing some time steps, right? Time steps. Let's do s is equal to sinusoidal time embeddings, just like that. And let's do the time embed dim is 128. And the second one, let's just set it to none. We haven't talked about what this is yet. We'll see that in just a second. So let's say our time steps is going to be torch.tensor, and let's say it's just 1, 2, 3. So time index 1, time index 2, time index 3. And we're going to pass into here our time steps, just like that. So if we print out our time steps here, we should see 1, 2, 3. So there we go. And what we want isn't really the index, but the frequencies at 1, 2, 3. So let's go ahead and access that. Our time step freaks, the time step frequencies, is going to be the time step frequencies. Actually, it might be easier to show this one step at a time. So let's just do one of them at a time. So if we print out our time steps dot shape, and then print out our self dot inverse frequencies dot shape, inverse frequencies, just like that. There we go. You can see it's 3 and 64. We have 3 time steps here, and we have 64 frequency. Because the reason it's 64 here is because we have, yes, because we went from 0 to 128 in chunks of 2, right? 0 to 128 in chunks of 2, so that's 64. And so all we need to do is multiply these things together, because we want to do the position, so that's 1, 2, 3, times this constant that we create. We did 1 over this, we sort of multiplied by the position dimension. It's just we can't multiply them directly because the shapes won't really work out. So let's just quickly see how we can do that. If we do a dot unsqueeze 1, so add an extra dimension here, and then a dot unsqueeze squeeze 0, that adds an extra dimension here, we're going to be multiplying every single time step along with every single frequency for all 64 frequencies. Right? That's the main idea. So we're multiplying every time step, so 1, 2, 3, with every single frequency. So we're getting every combination of them, and that's important. So what this will end up looking like is time step frequencies is going to be time steps dot unsqueeze 1 times self dot inverse frequency dot unsqueeze 0. And so now if we print u out, let's delete all of u, you'll get this, a 3 by 64 matrix. That's basically exactly this. So for position 1, so for the first one here, we're going to have all 64 things here because it's every other one, right? For position 2, we're going to have all 64 things. For position 3, we're going to have all 64 things. But we don't want 64, we want 128 because we need to essentially concatenate the sign of these frequencies and the cosine of those frequencies together. So let's go ahead and do that last part. We're going to do embeddings is equal to torch.cat, and we're going to concatenate onto this our sine. That's going to be right here, torch.sine of the time step frequencies, and then torch.cosine also of the time step frequencies. And we'll do it along the last dimension. So if we print out our embeddings.shape, you'll see that we have a 3 by 128 embedding. Now why is that? Because for every single sample, or for every single time step, we're representing it by a vector of length 128. The first 64 of those time steps, right? The first 64 values of this embedding vector of length 128 comes from the sine of the frequencies. The second set of 64, so the second half of the 128, comes from the cosine of those frequencies. In the original implementation, they'd interleave the sine and cosine again. So like the first one's sine, the second one's cosine, the third one's sine, the fourth one's cosine, dot, dot, dot. But this is just an easy way that gives you exactly the same result, because linear layers don't really care about the order of the features coming in. It's just about having the features. So there we go. We have our sine and cosine all stacked together, ready to go. Now, this is fine, but typically we have another linear layer, or at least something on top of this. So that's what we're going to be implementing now. The time MLP, very simple, sequential. It's going to have a linear layer that goes from nn.linear. It's going to go from time embed dim to the scaled time embed dim. And this is completely up to you for what you want to use. And then typically we use a CLU activation function here. So most places you'll end up using CLU, so there we go, we use CLU. And then we'll have another linear layer that's going to go from scaled time embed dim to scaled time embed dim. And again, we'll have another CLU activation layer. So again, we use it this way because it seems to, it's been shown to work best in practice using the CLU activation. So we now need to define the scaled one. So that means we're going to be producing a vector of 128, but then using 2 linear layers and 2 activation functions to scale it up to 256. And so the final step will be embeddings is equal to self.time MLP embeddings. And we can now return embeddings. And we can look at the shape of this, and it should be 3, because we have 3 time steps, by 256, a 256 length vector representing the data, basically the positional information at that time step. So this is not trainable, but these parameters are trainable. That's the main idea. Nice, so the sinusoidal time embedding is done. So you've written a scheduler, a transformer, and the time embeddings. Now it's time for the most annoying part, the UNET. Again, the UNET is very similar to what we had done before, but we just need to make sure we, we'll just redo it again. I'll again be going a little bit faster, just because I've done this before. Go ahead and take a look at that earlier video if you want some more details. But let's go with the first piece. So a UNET is basically, if you don't remember, you have to do a bunch of convolutions to downsample your image, and then a bunch of either upsampling or transpose convolutions to go back to the segmentation map. So that's the structure, but what makes a UNET more annoying to implement than something like an autoencoder is because you have to keep track of the input shape to concatenate it on, so then you can actually process everything. So these skip connections is what makes the UNET mostly annoying to implement, but we will do it. So the first step is the residual block. So each of these convolutions is actually a stack of a couple convolutions, which we'll be calling the residual block. So let's go ahead and implement that residual block, which should just be a stack of 2 convolutions with a potential residual connection between them. So let's go ahead and do that. Class residual block and then module def init self in channels. It'll have some out channels. It'll have some group norm num groups. This is if you're using group normalization, which we'll be doing, because it seems to work best for diffusion, rather than like bash norm has its own issues, but it works better than instant norm and layer norm. So we'll be using group norm here. And then we have our time embed dim, and you'll see why we do that as well. super.init. We'll have a forward method. Good. All right, so step one, we need to define all of our stuff. So our time embed dim, let's call this RB, is residual block. Let's say the in channels is 64, the out channels is 64. Our group norm num groups, let's say it's 4, it's 5 or 16. And let's do the time embed dim is going to be, we set it to 256, right? That's the output embedding dim of our time embeddings. So that's going to be 256. There we go. And so the first step is going to be this. We want to add our time embeddings into the residual blocks. So what does that exactly mean? Our residual blocks, we need to essentially inject some type of time information, that's our time embeddings, into these convolutions. And there's actually a couple ways of doing this, but let's go ahead and see what that looks like. Let's actually move you down here. Let's just do a quick example. I'm going to just copy this in so you can see. So we have some random image of batch size by 64 by 32 by 32, and we have some time embeddings, which is batch size by 64. So we're using 64 numbers to represent the time embeddings for every image, because every image has one time step, right? We're adding some number of noise to it. And we want to essentially add this to this, which means we want to add a batch by 64, a batch by 64 to a batch by 64 by 32 by 32. So we have the same problem that we had earlier when we did the repeated unsqueeze, essentially. We need to add some dummy dimensions to our random time embedding. So we're going to add like a dummy 1 and a 1 here. And then we can just add our time information, inject the time information into this right here. And that's the key idea. So this should run just fine. So we have some 4 by 64 by 32 by 32. We had our original time embeddings, 4 by 64, but then we expand by adding 2 extra dimensions and then adding that, injecting that temporal information into our image. That's the key idea. But the only way this is going to work is if our time embedding here, the 64 here, matches the number of channels in the image. Because if this was 64, but our number of channels in the image was like 48, then I can't add these two things anymore, right? So if this was 48 here, the original image, it's going to throw an error saying that, hey, 48 must match 64. So that doesn't work out. So that's one caveat that we have to keep track of. That should be fine, because I can use a linear layer to take whatever time embedding dim I have and just match it to the number of channels that we want in the output. So let's go ahead and do that first. We're going to do self.time_expand. It's going to be a linear layer that's going to go from the time embed dim to the out channels to make sure our channels match. This will make sure that the embedding dim of our embeddings, the time embeddings, always match the number of channels of our image tensor, so we can actually add them together. We'll still have to do the unsqueezing, but that's still okay. And so that's the first step. And after that, it's a standard setup. It's going to be self.groupNorm1 is nn.groupNorm, so it's a group normalization. And we're going to have group norm num groups and then in channels, right? That's all the information it needs to do the group normalization. And then we'll have a convolution, right? Con1 is nn.con2d. It's going to be in channels to out channels. And then the way I like to do it, of course, there's a lot of ways you can do this, but the way I like to do it is in residual blocks, I like to process the image. I like to change the number of channels if I have to, but I want to keep the image space, the height and width of the original image coming into this block, I want it to be the same. That just makes my life a little bit easier because I can essentially in some convolutions, I can do up and down sampling of the image space, the height and width. And then other convolutions, I can do up and down sampling of the channel dimension. And I just keep the two things separate so it just stays convenient. So we're going to do in channels, we have our out channels, and we're going to have a kernel size of 3 and padding equals same. That will ensure that the input height and width and the output height and width are identical. And then again, we're just going to repeat this one more time. We're going to do another stack of convolutions. Again, it's going to be a group norm 2, It's going to be group norm norm groups. Instead of in channels now, it's going to be on the out channels, right? Because it's on the second set. And again, this is going to go from not in channels, but out channels. It's going to go from out channels to out channels. Kernel size is 3, padding is same. So there we go. And that gives us almost everything we need. We'll add the last thing in just a second. This should be conv2. Right, so now we're going to do our residual connection is x, right? We can go ahead and store that here so we can add that on later. So first, our time embed is going to be self.timeExpand time embeddings. Let's create some random data. Let's do rand is torch.randn, batch size of 4. This is going to have, let's see, I set it to have 64 input channels, so 64 input channels, and then I have, let's say, a 128 by 128 image. And then we have our time embed is going to be torch.randn, and we'll have a batch size of 4, and each sample will have, let's say, a time embedding. I set it to 256, so this is going to be 256, which is a problem because our output number of channels is 64. So this convolution is going to have 64 channel output, this residual block. But we have 64 channel output, but we have 256 embed dim. So with that same issue from before, I can't add them together. So that's what this first linear layer will handle for us. So into this forward method, we're going to pass in time x and the time embeddings. So let's go ahead and do that into here. We're going to add in rand and time embeds. So if we print out our time embeds.shape, this basically reshapes it, in this case, to 256. So we want this to go to out channels, which I have set to, let's see, oh, it should be time embed. There we go. To 64. So this linear layer took the 256 length vector and projected it to a 64th length vector because 64 matches our output number of channels. So we're good to go there. And so now that we have that, let's just do our standard setup. Self.group norm group norm 1 x. X is f.silu activation, so silu activation x, and then x is again equal to self.con 1 x. So that's our group norm, do an activation, do a convolution. And now that we've done that, let's go ahead and inject in our temporal information. So we print x.shape and print our time embed.shape. You'll see what we are talking about here. So this should be con1. There we go. So our x.shape is this 4 by 64 by 128 by 128. Our time embeds is just 4 by 64 now, because we projected the 256 to a 64. So we just need to add those extra dummy dimensions in, 1 and 1, to add it to this. So let's go ahead and do that. So it's going to be x is equal to x plus our time embed is what we want to add, but we're going to do dot unsqueeze -1 dot unsqueeze -1. And that's going to go ahead and add those extra 2 dimensions in, and we will be happy to add them together. No problem there. Good. Print x.shape should just be that, but we've injected our time information. So now that we've done that, let's do our other convolutions, the second set. X is equal to self.group norm 2 x. X is equal to f.silu x, and finally x is self.conv2 x. So we've passed it through the second set of convolutions. And now all we need to do is that we can print out our x.shape and our residual connection.shape. You'll see that this and this are the same shape. So I can finally do our x equals x plus self.residual connection, or sorry, x plus just residual connection. Return x. So inside this one residual block, we have 2 convolutions, and we have a residual connection kind of going around the convolutions, and we are happy. But we're almost happy because there's actually a bug here that I haven't mentioned yet. Notice that we have a, let's call this out. so it doesn't print out. Okay, so notice that we have the same number of in channels and out channels, right? So in channels and out channels are 64 and 64. What if I make it 64 and let's say 512? This is going to throw an error saying, hey, I can't add things together. So what's exactly going on here? We have a print x.shape and print residual connection.shape. So the problem is that our new data, so let's comment u out, not connections, connection. Our x that went through all these convolutions is now has 512 channels, okay? But the original x, the thing that we stored as residual connection, has only 64 channels. So I can't actually add things together if there's different number of channels. And to handle this, we just add a quick resizer if we need it. So we're gonna do self.resize channels is equal to nn.conv2d. And this is gonna be a simple in channels to out channels and kernel size equals 1. So it's just a 1-by-1 convolution to resize the number of channels from 512 or from 64, the original, up to 512, so we can safely add these things together. And this will only exist if in channels does not equal to out channels, right? So only if the channels are changed. Otherwise, it's just an identity, right? Identity doesn't do anything. So if in channels is the same as out channels, then we don't need to bother with this line. And so there we go. And so instead of just directly adding x equals x plus residual connection, we'll have a quick self.resize channels around here as well. And if we need to do it, then it'll access a convolution. Otherwise, if we don't need to do it, then it'll just be an identity, which doesn't do anything. So good. We now have our residual block. So the residual block, the entire purpose of it is to process our data, keeping the height and width resolution the same, but potentially changing the number of channels and also injecting temporal information into our model. And this is where that happens. And so every single residual block, so every single block in our UNET, we're going to be adding that temporal information in. So we'll see how that's implemented a little bit later. Next, upsampling. So of course, downsampling is easy. We can just do a stride of 2. So we'll see what that looks like a little bit later when we actually do downsampling convolutions. But upsampling, we need to actually, do it in there's 2 different ways of doing it. We can either do transpose convolutions, or we can just use upsampling followed by a standard convolution. The second method is preferred as it leads to better image generation. Transpose convolutions typically lead to some type of a tiling, checkerboard, artifacting pattern in generated images just because of the way they work. So we'll be using this instead. And it's actually easier to implement this anyway, so it's fine. For a new class, upsample block, and in .module, definite, self, in channels, out channels, right? So the entire job of this upsample is to potentially change the number of channels if we want to, but also just upsample the image resolution. So there we go. So to do this, all we're going to do is self.upsample is going to be a first nn.sequential. It's going to be a stack of first nn.upsample. Standard bilinear upsampling. Scale factor equals 2. So we're going to upsample always by a factor of 2. Because we'll always downsample by a factor of 2 as well in the UNET. And then nn.conv2d, 2D convolution, with in channels, out channels, and then our kernel size is 3, stride is 1 by default, and padding equals same. So all we're going to do is make sure that the number of channels may change in our upsample. We'll see that later. But our image resolution, if we started with a 64 by 64 image, our upsample is going to upsample it to a 128 by 128, and then this convolution will learn something about that upsampled image, but it won't change the 128 by 128. It could change the number of channels, but it won't change the image resolution of it. So we're good to go there. So this will be just quickly a forward self x, and we can just do a return self.upsample x, just like that. So that's going to go ahead and upsample our images by a factor of 2. So now the hardest part, implementing the UNET. I'm going to implement this exactly how I implemented it in the original UNET video I made, just to keep some consistency. But the annoying part of UNET isn't really the convolutions, but just keeping track of stuff for the decoder, the upsampling. Because notice that in a UNET, we have a convolution, convolution, convolution over and over again, or these residual blocks over and over again. Every once in a while, we're going to downsample them. The pattern I typically use is like you do a residual, then a downsample, then you do some more residuals, then another downsample, so on and so forth. But we need to store these temporary or these intermediate outputs. Just keep them on hand. And so when we upsample them, we're going to take the output of the bottleneck, basically the most compressed form, do a convolution to upsample it, and then concatenate that information on. So we're going to concatenate all this on, and that convolution has to accept that stuff. And then we're going to go through some convolutions. Again, concatenate it on, go through some convolutions, concatenate it on, go through some convolutions. So this is not hard. You just have to keep track of the number of channels and the image space of everything. Because if this has 128 channels and is 32 by 32, and then our bottleneck outputs 128 channels, that's 32 by 32, then I can concatenate them together, right? Because they're the same shape. So I have 128 channels here, 128 channels here, leading to 256 channels here, again 32 by 32. But let's just kind of keep in mind what's going on. Our next one is 128 channels, that's 64 by 64. So I need to make sure that when I take my 256 by 32 by 32, regardless of what the channels is, I need to make sure when I pass through these convolutions, I upsample my 32 by 32 to a 64 by 64. So I can take my 64 by 64 here and concatenate it to the 64 by 64 here. So we just have to ensure that the output shape of each of these things matches whatever the shape of the stuff we stored here is. A little bit finicky, but not too hard. The way I like to do this is essentially creating a config and then building the model after that. So let's just go ahead and put it together. This is going to be identical, essentially, with exception of the, it's essentially the same as the UNET implementation we did earlier in one of my previous videos, but we'll be adding in attention and that sort of stuff. So a couple of little details, but nothing too different. So we're going to do self. We're going to have our in channels. That's typically 3, right? 3 channel images. Our start dim is going to be 64. So this is going to say, I have an image of size 3, and we're going to project it straight to 64 dimensions. That's weighs 3 to 64. And then the question is, how many residual blocks do you want to do? Or how many stacks of residual blocks do you want to do? So what we're going to do here is we're going to have a dim mult is going to be equal to 1, 2, 4. Well, so what this is saying is we're going to have 3 different levels to our, so what do I mean by levels? Let's look at the original UNET picture. This unit has 1 level, so 1 convolution, 2, 3, 4, right? There's basically 4 downsamples happening and then 4 upsamples happening. In this case, we have 3 levels here. So if we start with an image of 256 by 256, we'll downsample it by half to 128 by 128, downsample it by half to 64 by 64, and then downsample again by half to 32 by 32. So we have kind of these levels of convolutions, and this is how we're defining it. So we're saying that we're going to have 3 levels, and the number of channels in each level is determined by the scaling factor. So the first one's going to have 64 channels, as it's 1, so 64. The second one's going to have 2 times 64, so 128. And the third one's going to have 4 times 64, right? So that's how many channels will be in each of those levels. But we can have as many residual blocks as we want. So we can do residual blocks per group. So in each of these, sure, we're doing 1, 2, 4, like we have 3 different levels. But in each level, how many residual blocks do we want to have? And this is an easy way to make your neural network much bigger to train, make a bigger model to train deeper networks. We're just going to stick it to 1 right now. We're going to have group norm. Now groups, this is our group normalization. Groups, let's just set that to 16. And then the time embed dim is going to be 128. So we're going to say that the input time embedding that's going to be coming into the model is going to be 128. And this 128 has to be resized via our method from earlier, right here. It'll be resized to the correct number of out channels by this linear layer in every single residual block. So we're going to be adding this time embedding dim to every single residual block. Good. So let's go ahead and implement it. So super self.init. So first we're going to do self.input image channels is going to be in channels, right? Let's go ahead and store that information. And our channel sizes is going to be start dim times I for I in dim mul. So let's go ahead and do UNET equals UNET. Everything's predefined. And so we print out our channel sizes. You'll see the first block of however many residual blocks we want. So first group of however many blocks we want, it's going to be working with 64 channels. Then the next one will be 128, the next one will be 256. And it's up to you. You can add as many or as little as you want. You could have a bunch of 2s in here and make your neural network much, much deeper. But the key idea is that we're going to be downsampling by a factor of 2 every single time. So there we go. That's our channel sizes. And then our starting, let's just store some information. Starting channel size, ending channel size is going to be our channel sizes 0 and channel sizes -1, just like that. And so let's go ahead, like I mentioned, we have to create, the way I like to do is just create a config where we can keep track of everything, and then using that config, we can build our actual convolutions. So config's up first. Let's do the config for the encoder. So self.encoder config. Make an empty list. And we're going to do for index dimension in enumerate channel sizes, right? So for each one of these, right? So that's this, right? So the 0, 64, 1, 128, that sort of stuff. We're going to do for blank in range residual blocks per group. So how many residual blocks do you want in the thing? That's determined by this. We're going to do self.encoder config.append. And we're just going to store some information here. The main things that I care about is what's the input dimension and the output dimension. In this case, it's going to go from 64 to 64 because that's what I'm working with. And then we have a residual. I'm going to call this a residual because it's going to be a residual block. So this is just going to store some information for me. So we can do print self.encoder config. Looks like I need to change that to lowercase. And there we go. So we have our residual block going from 64 to 64, residual block 128, 128, residual block 256, 256. Okay, good. So we're on the right track, but we're missing something because we need to make sure that after every single block, we downsample by a factor of 2, right? So let's go ahead and do that. So we can do as many residual blocks as we want over and over again, but once we've completed this, we need to go ahead and downsample by a factor of 2. Self.encoder config, and then we're going to do .append. And it's up to us, again, what we add. So I'm going to go from D to D, and I'm going to call this a downsample block. So there we go. So that gives us everything we need. And then finally, what we need to do is a self.encoder config. Now's our chance to add the new thing that we didn't have previously in our first UNET implementation. That's attention, right? So we're going to go ahead and add in attention, and all we need for attention is what is the input number of channels in channels. That's just the dimension that we're on. We'll just call this attention. So there we go. So now we can see that we have a residual block, we have a downsample attention, residual downsample attention, residual downsample attention. If we changed our number of residual blocks per group to like 4, then our neural network just becomes deeper. We have a residual, 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 downsample attention. Again, residual, 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 downsample attention, ... Right? So we repeat that over and over again. That's just an easy way of making your neural network deeper. Good. Now, the last thing we need is we need to make sure that we are changing the number of channels. Like we're going from 64 to 64, 64, 64, 64, but then we just jump to 128 to 128. So that doesn't work out. We need a transition convolution to take our data from 64 channels to 128 channels. And that's our opportunity to do that here. And of course, we're going to do that at every single one of our channels, except for the last one, because when we're at the final block, we don't need to continue going. That's it. We're at 256. There's nothing else after that. But we need to make sure our 64 goes to the 128 and make sure that our 128 here goes to the 256. So we need a transition convolution to change the number of channels as needed, but everything else can stay the same. So we're going to do if index is less than len channel sizes minus 1. So if we're not on the last one, we're going to do self.encoder config.append, and this is just going to go from D to, and let's add one more. So it's going to go from D to channel sizes index plus 1. So what is the next channel size we need to go to? And then this will again just be a simple residual block. So now we have a residual block going from 64 to 64, then a downsample that's going to keep the same number of channels but downsample by a factor of 2. We're going to compute attention, self-attention, on that compressed image, and then we're going to upsample the number of channels from 64 to 128, leaving the image space alone, but our channels are now 128. And now that we're 128, the next residual can pick up from where it left off, right? 128 channels, no problem. Again, we downsample by a factor of 2 again, compute attention again. And then we upsample from 128 to 256, right? The number of channels gets upsampled from 128 to 256, so we're ready for the next one. But at the last one, we don't need to do another upsampling of the channels because, well, we're at the end. There's no reason to add anymore. And that is essentially the setup for the encoder. No problem there. The bottleneck is very simple. It's just some residual blocks, right? So that's our, let's go back here. So we have our encoder that we've implemented. Now we have a bottleneck that can be however many convolutions you want. And then we have our decoder, which we haven't gotten to just yet. So we're going to do self.bottleneck config is going to be an empty list. And this will very simply be for blank in range residual blocks per group, however many residual blocks you want. We're going to do self.bottleneck config.append, and all we need to store here is we're only in the ending channel size, right? So we're already at the end of our channel sizes, right? We've worked our way to 256, which is the last one. So this can only go from ending channel size to ending channel size. So let's just do that. And this is a residual block. And we are good to go. That is our bottleneck. Now, for the decoder, this is where it gets a little bit more challenging. So the typical structure of your UNET is the decoder is just a mirror image of the encoder. So we're just going to make sure they're very similar to each other. And the easiest way to do that is just taking our encoder config and reversing it. So what we're going to do is store outdim is going to be ending channel size. And this is just saying that we're currently at this channel, right? So we're currently at the ending channel size, so that's what we have. And then our reversed encoder config is going to be our self.encoder config that we just made. So we're going to turn it around because we're just going to do exactly the same thing, just going backwards. So we're going to do self.decoder config is an empty list, and we're going to do for idx. And remember, in our encoder config, it's a tuple of two things. We have some metadata and then the type of layer that it is. So let's just do that. It's going to be metadata and type. Let's do L type, like layer type. In enumerate, reversed encoder config. So we can print out index metadata L type, and you can see exactly what we have here. Looks like I spelled this wrong. There we go. So we can see these were all the layers in our encoder, but in reverse order, right? You can see that we started here and went here. That was our encoder, but now we're just doing it backwards. And our goal is just to make the exact same looking thing, just going in the reverse order. So let's go ahead and start doing that. We're first going to do if type does not equal, or let's do L type does not equal to attention, right? So this is not an attention module. Then we can go, because attention modules are easy to work with, there's really nothing to do there. So if it's not an attention module, let's just handle that condition first. We have first the encoder in channels and encoder out channels is equal to the metadata, right? Because if it's not attention, so in everything else, we have a tuple of two things. We have the input channels and the output channels of that convolution. And so we can now do self.decoder config.append. And here is where it gets tricky. So let's actually make this as clear as possible. Append. We're going to have a tuple. And in this tuple, we're going to have two things. The first thing is the convolution that the decoder, the first convolution that the decoder is going to have, is not going to be just the output from the bottleneck, which we know has outdim, right? However much that is. So it's not just the output from the bottleneck, but we're also going to concatenate the output of this from our model, right? So that's the key idea. The output is not just the bottleneck. It's going to be the concatenation of the output of the bottleneck and the thing from the encoder. And let's just kind of go back here. Basically, we need to make sure that our number of channels is equal to however many channels the bottleneck is outputting plus the number of channels that was in our encoder, because that's what's going to concatenate together to go to here. So we just need to make sure that our currently the outdim, which is the output dimension of the bottleneck, right? What the bottleneck produced is 256, the ending channel size. And we know from this convolution right here, so ignore the attention one right now, let's just look at this one because we're looking at if it's not attention. We know this convolution right here outputted 256. So I know I'm getting 256 from here, and I know I'm getting 256 from the bottleneck, so I can add those things together. So this one's going to be the number of input channels is going to be outdim plus encoder out channels. And we're going to make sure that this is kind of a mirror reflection. So we're going to go from this 256 from here and 256 from the bottleneck, and we're just going to go back. The number of output channels is just going to be 256. So whatever the input channels of the encoder was, that's going to be our enc in channels. And that's going to be our input channels and output channels. And then this is just going to be a simple residual block. Just like that. So that's the key idea of our attention, or of our residual connections, how we're managing them, these skip connections. We're just keeping track of what's coming out of the previous layer. We obviously have to update this value in just a second. We'll get there. But what are we getting from the previous layer, and what are we getting from our stuff that we stored that we're going to be concatenating on? And that's where this is coming from. Now, one key thing is that if we had done a downsample, so if we had done a downsample here, then we actually have two things we need to do. We need to both match the number of channels this way, but then also upsample the image, because if our image was downsampled here, then we need to upsample it here so the image is actually matched, the space matches. So again, it's all kind of a reflection of what we had done. So we're going to do if type, or let's do L type, is a downsample, right? So if we did a downsample in the encoder, we need to now upsample it in the decoder, so it remains the same shape. So self.decoder config.append, and this is going to now be a let's see, enc in channels. So that's where we're at, right? We went to enc in channel, so it's enc in channels to our enc in channels. We're not going to change the number of channels here, keep that the same, but we're going to upsample the image space. And so that will be handled by that keyword in the future. And so that's the key idea. If we're not doing attention for convenience, we can go ahead and extract our input and output channels, and we can go ahead and just make sure we manage the number of channels here by adding everything together that we know is how it is. So the output dim plus how many channels do we get from the output of the encoder that we're concatenating on. And then we're going to send it to the in channels of the encoder, just so it remains kind of like a mirror image. So we'll see what that looks like in just a second. Now that we've gone ahead and done this, this convolution, right, this set of convolution will output enc in channels. So this block of the decoder will output enc in channels, encoder in channels. So that means our new out dim is going to be enc in channels. And there we go. That's the new output dim will be the number of output channels from our block, or the the corresponding encoder input channels. Good. So this is, again, this is probably the most annoying part of all of this code. Now that that part's out of the way, we're kind of in the home stretch now. So else, right? If we're in an attention module, so attention only had in channels equals metadata, right? So that's all it was. Our metadata was just a single number. That was just in channel. So there you go. And then self.decoder config. If we did attention in the encoder, then we want to do attention again in the decoder to keep it the same. Append, and this is going to be in channels, and it's going to be an attention block, just like that. And so now we will end up having basically everything we needed. So we can look at our print self.decoder config, and that's our decoder, right? Nothing too crazy. All of this is well and good, but there's actually one more residual that we haven't talked about yet, or one more basically skip connection that we haven't talked about yet. Notice that we directly started here from 64, right? So we went from 64 to 128 to 256. We just straight started there. But we actually have one more convolution that we haven't defined just yet, but we will. That's the thing that takes us from the 3 input channels of the original image to the 64 channels. So that convolution that goes from 3 to 64 will also have a skip connection, right, on the other end. So we just have to make sure we include that in. We can just toss that in manually. So we can do self.decoder config.append. This is going to go from starting channel size, and we're doing it times 2, right? So we're gonna, okay, so the main idea here is we need to add in an extra residual block for the residual from that first input convolution. And we know that that initial convolution will have the starting channel size, like whatever we set it to, and the output of the decoder will also have starting channel size. So the final residual block will need to go from 2 times starting channel size to starting channel size. So what does that mean? I know I'm getting a 64 channel output from the decoder. I also know that that very first convolution that's going to upsample from 3 to 64 channels will also have 64 output. So if this is giving 64 output and this is giving 64 output, then this thing must be 2 times 64. That's the main idea. So that will always be the same no matter what, because that's just how we built it, right? And we can just put it back to starting channel size. And this will again be a residual block. Simple as that. So now that we have everything we need, we can go ahead and actually build the model, because all we've done is kind of define some configs here. But based on these configs, we have everything we need to implement our actual UNET. So let's go ahead and do that now. So we're going to do actually build model. All right. We're going to do self.con in project. So this is that very first convolution I was just talking about, and end up conv2d. It's going to go from self.input image channel, so 3 channels in this case, or whatever it is, to the starting channel size, which is 64 in our case. And then we'll have a kernel size of 3, and padding equals same, right? To ensure that we have the same image space, but we've just changed the number of channels from 3 channels to the 64, basically our start dim that we set here. Now that we have that, let's go ahead and define the rest of it. So our self.encoder is going to be nn.module list, and we'll just loop through our metadata. So we're going to do for metadata type in self. And not type, let's do L type again. In self.encoder config, if L type, right? So if we're working with a residual block, right? So if it's a residual block, then we're going to do in channels, out channels is equal to the metadata. That's what we have in our metadata. We have the number of input channels and output channels for each of those residual blocks. And actually, this one should just be called residual, not residual block. There we go. So in channel and out channel. And we can then go ahead and define a convolution. Self.encoder.append and we'll do the residual block that we defined earlier. And it's going to have in channels, out channels, the group norm num groups, whatever it's set to, and then the time embed dim, whatever it's set to. And that will be the residual blocks. And then up next will be our downsample blocks. If L type is downsample. Okay, no problem. We just need to do a convolution. So in channels, out channels is equal to the metadata again. And we can do self.encoder.append. And how do we do a downsample by a factor of 2? We do a stride of 2, right? We just stride by 2. So we can do self.encoder.append and n.conv2d in channels, out channels. We'll do a kernel size of 3, a stride of 2. So it's actually defined. Kernel size equals 3, stride equals 2, and padding equals 1. So this will downsample by a factor of 2. Otherwise, if type is attention, L type. Right, so if we're dealing with an attention module, then it's very simple. In channels is equal to the metadata, because that's all we had for the attention. And we can do self.encoder.append, and this will be the transformer block in channels. There we go. So nothing too crazy. We're good to go there. We could probably make this a little bit more complicated because the transformer block had some more stuff here, but we're just going to stick to these defaults of 4 heads with an MLP ratio of 2, so it's fine. But technically we should be passing that information in here as well. So that goes ahead and defines our encoder. We can go ahead and look at our UNET, see where we're at. So here's all the blocks we've already defined. And now that we have our encoder, you can see we have a residual, we have a downsample convolution, a transformer, another residual, another downsample convolution, another transformer, so on and so forth. So it's just kind of repeated on top of each other. Good. Now that we have that, let's move on to the next part. That will be our bottleneck. So let's do our self.bottleneck. This one's pretty easy. Self.bottleneck is, again, nn.module list. It's going to be a list. And this is going to be our for in channels, out channels, in self.bottleneck config, right? So we can loop through the bottleneck. This is going to be self.bottleneck.append, and this will just be this residual block one more time, right? It's just a residual block over and over again. So there we go. In channels, out channels, group, the number of groups in a group norm, and the time embed dim. So there we go. That is our bottleneck. Lastly, we have our decoder. So our self.decoder is equal to nn.module list. Again, for metadata, L type in self.decoder decoder config. Same as before. So I can actually go ahead and copy paste all of this in because this is no different from what we just had. Except this will be L type instead of type. There we go. So if it's a residual block, do a residual. If it's a upsample, then do an upsample. If it's attention, then do an attention, but it's just our decoder. So there we go. So now we have all of the layers. So it looks like I'm missing one thing. I did stide, upsample. I spelled this wrong. Was it above transformer? Sinusoid time embeddings. Here. Stride. There we go. So that is all of our convolutions in this specific model. Good. Now, if you notice, the final convolution outputs to 64 channels, we need our final convolution to go from 64 channels back to the 3 channels that we started with, right? The final convolution. So that should be relatively straightforward. We'll just add that in. We'll do self.conv_out_proj, the final output projection. It's going to be nn.conv2d. And it's going to be from the starting channel size, because remember, our final convolution that we manually added to our decoder outputs starting channel size, so 64 in our case. And it's going to go to the self.input_image channels with a kernel size equals 3, stride equals same, right? Or sorry, not stride, padding equals same, to make sure it stays the same size. And that is our final layer that we need. So let's go ahead and actually define it. So we're going to pass into our forward method, x and time embeddings. So we set our time embedding dim to 128, so let's just stick to that. So our data, rand, is equal to torch.rand some batch size by number of channels by, let's say, 128 by 128. And then our time embed is equal to, again, torch.rand n, and it's going to be some batch size by the time embedding, right? 128 is what we set it. So into this UNET, we're going to pass in our rand and the time embed. And that should give us everything we need to see how everything's working. So first, we need to do our encoder, right? We need to go through the encoder. But to do the encoder, we want to make sure we store these residuals, these skip connections, so we can concatenate them later. So first we're going to do x is equal to self.con_in_proj, right? That's our first convolution. To go from the 3 channels to the 64 channels, we can check x.shape. We went up to 64 channels from the original 3 channels, so that's looking promising. And we're just going to go ahead and store this in our residuals. Residual, and let's make it plural so it's clear. Residuals.append x. Go ahead and store that as a copy. And now we're just going to loop through our encoder one layer at a time, and then just pass our data through. So we're going to do for module in self.encoder, but what we do kind of depends on what we're actually working with. So we're going to do first if is instance. So if this module is a residual block, right? If this module is a residual block, then we're going to do x is equal to module. It gets x, it gets the time embeddings, because the time embeddings are injected into the residual blocks. And then we can do residual.append x, just like that. Else, so elif is instance module, if it's just a standard nn.conv2d, like the first layer, like the very first convolution layer, then, or any other layer that's in here, if it's just a standard convolution with nothing else, like our downsampling or whatever, then just go ahead and do x is equal to the module, just pass our data in, and then again residuals.append x. Because in convolution layers, there's no time embeddings. Time embeddings are only for the residual blocks. Otherwise, right, for any other kind of layer like the attention layer, just do x equals module x, and we are good to go. Append a p p e n d. There we go. And that's going to go ahead and store all of the residuals that we need in our residual kind of list. Now that we have that, let's go ahead and go through our bottleneck for module in self.bottleneck. X is module, X time embeddings, right? That has to go in there because our bottleneck, everything is just residual connections or residual blocks. So all of them get the time embeddings. And then finally, our decoder for module in self.decoder. And this is where it gets a little bit tricky. We're first going to do if is instance, right? If the module is a residual block, no problem. Then we're going to do our first residual tensor. It's going to be residuals.pop. So we're going to grab the last thing off this list. We're going to remove it from the list and store it in here. That's the residual that we're going to need to concatenate on. And so x is not just the original data x coming from the bottleneck in this case, for that first thing in this for loop, but it's also going to be this residual tensor concatenated on. So x is going to be torch.cat. We're going to concatenate on. The residual tensor onto x, And we're going to do it along the dim equals 1, so along the channel dimension. So channel 0 is batch, dimension 0 is batch, dimension 1 is our channels, along the channel dimension. Now that we have that, we can then do x is equal to module x time embeddings, just like that. Otherwise, anything else in here, we just do x equals module x. It's only these fancy residual blocks where you have to do all this extra work to get things to attach, because we only store them for that anyway. So we are good to go. Okay. So now we can check. So that's the final output of this, all of this stuff, right? So we've gone ahead and we've actually, so we can actually check here. Print residual tensor.shape. So those are all of the residual blocks, residual connections that we stored from the encoder, and we end up concatenating them on, so we can do x.shape, and then we can print out x.shape. So you can see we had a 256 residual tensor that we came from our encoder, and we had 256 from the bottleneck. These two things concatenated together to make 512. And then we had a convolution that took it from 512 to 256. In the next one, we had a 256 from our encoder. We had 256 from here. Again, 512, dot, dot, dot. We just repeat this over and over again until we get through our entire model. So there we go. That's the entire UNET concatenation process happening. Now that we have that, we can go ahead and do our final convolution, x equals self dot conv out proj x, print x.shape. Now we have our 3 channels, right, for the actual image space that we're working with, and we can return x, and we are done. That is the entire UNET implementation. Good. Now that we have that, let's go ahead and put all of the stuff we've done together into a single diffusion model. So we're going to do class diffusion and then dot module. Definitely. Now I'm going to copy the init. There you go. So that's the model I trained. 3 input channels, dim mults, how many blocks per group, group norm, that sort of stuff. So everything else is the same. All right. So now we're going to do super.init. And we just need to define a couple things. So again, I'm just going to copy all of the easy stuff that doesn't really... Actually, to be fair, I can just copy all of this. There's nothing in here. So we have our in channels, the starting dim, dim mults, and just making copies of these. We then have our time embedding dim, and then we have our scaled time embedding dim. Because remember, our time embed dim might be 128, but we could set our embed dim ratio to 2, so then it's actually 256. So there you go. That's our final time embeddings that pop out of the sinusoidal time embedding will be 256. This. And so our sinusoidal time embeddings, there we go, that's where we define here. And then we of course have our UNET, which is right here. And the time embed dim will be the final scaled time embed dim from our sinusoid. So in this case, it'd be 128 times 2 or 256. So we're using 256 dimension vectors to represent every single one of those time embeddings. Now that we have that, simple forward method, def forward self x, and actually this is not going to be just x, let's make this a little bit clearer. These will be the noisy images, and then time steps. And our goal is, given the noisy image, and how many time steps of noise is it, can I predict the noise that's actually there so I can denoise it in the future? So it's going to be time step embeddings is going to be the self.sinusoid time embeddings, pass in the time steps, and then we have our noise pred. Our prediction for the noise will be the self.unet noisy inputs and time embeddings. And if we quickly take a look again over here in our formula, notice that our prediction, so this term here is our prediction for our amount of noise, and the amount of noise depends on the noisy image, so x noise for t steps, as well as a noise vector that represents the tth time step. So there we go. That's what this is, the noise pred. And then we can return our noise pred, right? This is our predicted amount of noise for this specific time step. And we are good to go. So that's basically all the hard work. Now we just have a little bit more work to do in terms of training and visualizing. So let's write the visualization script very quickly. This is going to be at torch.nograd. And it's going to be def sample plot image. And actually, let me just copy a little bit of this, just so you don't have to watch me type all this. There you go. So this is going to be very simple. It's just a very simple plotting script that we're going to use for training purposes. The first one is step index. So we'll be training the model for, let's say, 50,000 steps. This is just saying which step are we on, so I can log the image for that step. How many time steps are we? So this is total time steps. This is the 1,000 diffusion steps that we have, so total time steps. The sampler is the diffusion sampler that we wrote earlier, so that's fine. We have our image size, num channels, the plotting frequency. This will make more sense if I actually show you. I'll just show you the results right now, and then we'll come back to writing the code. Basically, here we have, the way I said it is I trained for 500 steps with a 50-step interval, right? 50-step interval. So what that means is I have 500 steps here, but I only plot every 50 of them, giving me 10 pictures. So there's 10 pictures here, but that's because we're plotting image 0, image the 50th, the 100th, 150th, ... So we'll see what that looks like in just a second when we actually get there. Okay, so let's just keep going. We need to, so we have our model, a number of generations. Number of generations, how many pictures do I want to visualize? Path to save it, and then the device we want to do it on. And so to actually do our model, we need to be able to convert tensors back to images. We also haven't written the transform to go from images to tensors. So let's actually maybe write a little bit of that too. So we can do def train. Again, I'll copy paste a little bit of this right now just to make it go a little bit quicker, because there's nothing all that interesting about the training loop. I'll just work dir. And we'll do device is equal to CUDA if torch.CUDA.is available else CPU, right? Standard. And we're going to have a quick transform that's going to take our image. Now remember, images are between 0 and 1, but typically for diffusion, we're going to rescale them to be between -1 and 1. Okay, so to do that, we can do image to tensor. It's going to be transforms.compose, right? Standard transforms. And the first thing we're going to do is transforms.resize, make sure the images are in the shape that we want them in. That's going to be in, what do we call it? We picked an image size of 64, so it's going to be from whatever it is to a image size by image size, just like that. And then after that, we're going to have transforms.random horizontal flip. You can add other types of augmentation if you'd like. Transforms.toTensor, go ahead and convert it to a PyTorch tensor, right? And then finally, the most important one is transforms.lambda, and this is going to be a simple lambda function, t times 2 minus 1. So if our images are between 0 and 1, because all images, when they start out, will be 0 to 1. If we multiply by 2, that'll make it 0 to 2, right? So this will go to 0 to 2. And then if you subtract 1, then it'll be from -1 to 1. And so that's all this is doing, just making sure our 0 to 1 image is rescaled to -1 to 1. And then in the same way, if our data is being predicted on the -1 to 1 scale, right? So if our images are between -1 and 1, but we can only plot it between 0 and 1 because that's how we need to do it. That's what this is doing. So first of all, we're going to get rid of that extra batch dimensions because we don't need it. We then have this is just undoing that. So if our image is between -1 and 1, if we add 1, -1 and 1 will go to 0 to 2. And then if you divide by 2, it's back to 0 to 1. So this is just undoing this transformation here. Then go ahead and just put the channels last. And then go ahead and rescale it from 0 to 1 to 0 to 255, and then convert it to UNET and convert it back to a pill image. So a very simple sequence of transformations just to take our -1 to 1 image to pill images that we can actually plot. So there we go. Great. Great, now we have our images is going to be torch dot. So our images, when we inference, and this is the key idea, something we haven't talked about too much just yet. When we train our neural network, we're training it to denoise, right? Take noisy images and go back to the original one, which means when we're inferencing the model, we start with noise, pure noise, and we just denoise away. And again, that's seen here. xt, in our case t is 1000, start with a random Gaussian noise, and then just repeat this. And we already implemented this method here in our scheduler, right, to remove the noise. So basically everything is done for us. So let's go ahead and do that. So we can do torch.random. And how many images do we want? We want to do batch size. So this will be our, let's do num gens by the num channels. In our case, it's 3, but num channels. By image size. So it's going to be 3, or it's going to be image size by image size. So we're going to go ahead and just generate some noise in the shape that we want. And then we have num images per gen. It's going to be the total time steps, so in this case 1000, divided by plot frequency. Or in our case, if it's 500 and we have a plot frequency of 50, then we'll be generating 10 images, each at 10 image or 50 image intervals, right? So there we go. This way we can just visualize the denoising process. So again, going back to this is me starting with pure noise and then denoising it to an actual image, right? So that's what we're seeing here. And that's all well and good, but I actually wanted to visualize a little bit of that denoising process. So I'm plotting what's the fully denoised image, and then what does it look like after 50 steps of denoising, 100 steps of denoising, 150 steps of denoising, So I just wanted to see what that looked like. So that's why we have a little bit more effort here in the visualization, but no problem. And so we're just going to create a nested list here just to store these images in. So images to visualize is going to be a list for blank in range numgen. So let's create an empty list, and I'll just store in each of these lists all the pictures for that specific image, and then we'll have a list of lists essentially. So we're going to do for t in np.arange. What are we doing it? Total time steps. And so, okay, this is actually a good point. Let's do np.arange. Let's say we're doing 500 steps of noising. So this is saying that we have 0 steps, 1 step, 2 step, ... So these are all of my steps of noising that I can do. But when I denoise, I want to start at the end and slowly work my way back, because to denoise, we have to denoise it 1 step at a time. So from big T to 1. So in our case, from 500 to 1, or by default, from 1000 to 1. That's what we need to do. So if that's the case, we just need to reverse this list. Instead of going from 0 to 499, we want to go from 499 back to 0. So let's just go ahead and do that. For NP and arange, total time steps, but we're going to flip the list around, just like that. Now that we have done that, we can do 2 things. So first, we're going to do TS is, so these are times. It's going to be torch.full numgens t. So what this line is doing, and the way to show it off is probably the best way to do it is this. So let's say we want to generate 5 pictures, right? We're generating on 5 pictures, so that's going to be torch.full. This is going to be 5 pictures. And let's say we're on time step 50, right? So we're denoising, again, we're denoising in a batch. So we're saying we want to generate 5 pictures, but we're going to be denoising all 5 pictures at the same time. So let's say all of them are currently on step 23 or 24. That means these are our time steps. Every single picture is on denoising step 24. After we do 24, then we're going to go to 23. Now they're all on 23. Then we're going to go to 22. So it's just saying which denoising step are we on. Torch.full just makes a quick tensor that fills the shape I request with the t that I have. So that's all it is. And so then our images, or sorry, our noise spread is going to be model, pass in our images, make sure it's on the device, and t's also make sure it's on the device, just like that. So what I'm doing is I'm taking my images, which is currently pure noise, but slowly will be denoised, right, as we loop through this. So we're going to denoise our images, and we're going to give it the image, its current iteration, and then our time steps, right? Which time step of noise are we currently on? After that, we're going to do images. So our images were initially pure noise. Now our images is going to be equal to the sampler dot remove noise, that first method that we wrote. And that's using this right here, right? Remove noise. And to remove the noise, if you remember, what we needed was the images, the time steps, and our prediction, our current prediction of what that noise is. And then we're going to do if t% plot frequency is 0, right? So if we're there, then we're going to do for index image in enumerate images, just loop through all the images. We're going to do images to viz, grab the, remember it's a list of lists, so we're going to grab that specific list and then append to that list tensor to image. Go ahead and convert the tensor to an image on this specific image. We're going to go ahead and store that. The rest of this stuff is not all that interesting, so I'm just going to copy it. This is mostly just to plot the thing, right? So we're going to go ahead, grab our images to visualize. We're going to flatten the list of lists, and then we can plot them in a standard matplotlib plot. Nothing crazy. So I don't want to dig into that too much because it's unnecessary. So that is a quick helper function. The key idea here that I want you to see is to inference a picture, right? To actually generate an image, we need to for loop through every single time step to denoise our image. And this is probably the biggest limitation of the DDM paper, because although DDPM creates very high quality generations, it has an inference time penalty in that you have to loop through every single time step individually. So if you trained on 1,000 time steps, inference time, you have to loop through 1,000 steps of denoising to get your final image. These are some of the problems that other methods like DDIM have started to fix, where you have less inference time steps to get similar qualities of image, but we're not going to be looking at that today. Today is simple DDPM. So now let's go ahead and write our training function. Training will be very simple. We have our image to tensor, we have our data set. Let's do a simple image folder, and we'll be accessing the data celeb A. So this is just a folder full of images, full of like pictures of faces, right? So I'm just using the standard image folder to access it, nothing crazy. You can use any image data set you want, it's completely up to you. Just make sure you have something like this, and image to tensor is the image transform that we'll be doing. So we are good to go there. Now we need our train loader. Train loader is going to be the data loader data set, batch size equals batch size, shuffle equals true, num workers, let's say is 8, and pin memory, let's say memory is true. There we go. So now we have our data loader. So if we define our train function, transforms is not defined, transforms. Okay. Compose takes 2 arguments, but 5 were given. Let's see here. I think I need to have them actually nested in a list. There we go. Init got a transforms. This should just be transform singular, and we are good to go. So we can do for batch, and I'll have some labels, but we don't really care about it. And train loader, print batch dot shape. Make sure that works. And there we go. We have 64 images in the batch, right? So we have 64 images. Each image is 64 by 64, and there are 3 channels, of course. So we are good to go. Let's go ahead and define our model now. So our model is just the standard diffusion model. I won't change anything in it. And the in channels is going to be the num input channels, right? In this case, it's 3. Dot 2 device, make sure the model's on the GPU, and model, yeah, I can just copy this part. This is just to print out how many parameters are in the model. Num, oh, there we go. Oh, sorry. There we go. And looks like we have another big issue. So we have sinusoidal time embeddings, was it plural? There we go. So this model has about, what, 1, 2, 3, so about 24.2.3 million parameters. So very small model, nothing too crazy. And we can now do optimizer is torch.optim.atomw, or you can play with atom, it doesn't really matter, model.parameters, and pick some learning rate. And just to make life a little bit better, right, we can do a scheduler. So this is LR scheduler, just to not confuse it with the other scheduler that we made. Get cosine schedule with warm up. I imported this from Hugging Face, right? They have a bunch of nice schedulers built in. So optimizer equals optimizer, num warm up steps, let's just say is like 2500, and num training steps is our num training steps, right? So however many steps we have. And then we have our DDPM sampler. This is going to be the sampler that we defined earlier with the num training steps equals total time steps, right? That's going to be however many time steps we have in our DDPM. In this case, we're doing 500, but in more state-of-the-art models, it's typically 1,000. Good. So now that we have that, here's the last question. What are we exactly predicting again? We have to predict the noise. So our goal for this neural network is to predict the noise that is added to an image at a specific time step t. So here you can see we're doing standard mean squared error. So this is our prediction. So epsilon theta is our predicted noise vector of this noisy image at time step t. So this is essentially an expression of what is the noise I predicted. This was the true noise that I added, and here is the mean squared error, right? So we're doing the 2 norm. So why are we able to do that? Because if you remember again, in our scheduler, when we did the add noise method, we returned both the noisy image, which is what we had, and the noise itself that we added. So that's a key step, right? So this is the thing we're predicting from this. So given this noisy image and what was the number of time steps of noise that was added to this image, go ahead and predict that noise. So we can go ahead and denoise it. So let's go ahead and start actually adding in that stuff. So our loss function is going to be nn.mse loss. You're also MSE, mean squared error loss, is the standard loss function that's theoretically proven in this paper. But you could technically still use like mean absolute error or Huber loss if you want. And although it doesn't have the same like theoretical guarantees, it practically seems to work just as well, or even better in some cases. So you can play with loss functions a little bit and see. Progress bar, let's just do PDM, range, num training steps, so however many training steps we want. And we'll do completed steps is 0. So let's set our training scripts. It's going to be train equals true. And let's just start looping while train. We'll do training losses is an empty list. And we can then do for images blank in train loader, right? Go ahead and do that. We can do batch size is equal to images.shape 0. And step 1 is we have right now clean images. We have clean images from our data set. So the first step is let's just go ahead and noise them. Noise them for some random number of time steps. So how many time steps? Let's go ahead and random sample. So torch.randint from 0 to total time steps. We're going to random sample some number between these things in the shape of, just like we did before, just a vector, right? A vector of numbers, batch size. So for every single image, I'm going to random sample some number between 0 and 500. That's going to indicate how many steps of noise I want to add to that image. And so there's the first step. And so then we can do our noisy image, and noise is going to be the DDPM sampler dot add noise. We're going to add to our images, and we're going to add time steps worth of noise. So that's another key step. We are training our neural network by adding random amounts of noise to our image, right? So like a random time steps worth of noise to our images, and then asking our neural network to denoise them, right? By predicting the noise that we added. So this is our target, the noise. So then we have our noise prediction is going to be the model, noisy images. So we're going to pass in our images, and we're going to pass in, and of course it needs to be on the GPU, .toDevice, and we're going to pass in our time steps, .toDevice. So now our model's goal, the UNET's goal, is to take the images and how many time steps were they noise for, and try to predict the amount of noise that came from it. And then I can use that to denoise our images in the future. So our loss function, the loss is going to be the loss function between the noise prediction and the noise. And we're going to make sure the noise is also on the device when you do that, because the noise here is not on the device. So there we go. That's our loss. And then standard training, loss.backward. We should throw in some gradient clipping just for good practice. So torch.nn.utils.clip grad norm model.parameters. And we'll just clip it to a gradient of 1, or a magnitude of 1, a norm of 1. And then we can do optimizer.step, optimizer.0 grad, and then yeah, that's basically it. And we can also do scheduler. What did I call it? LR scheduler. Go ahead and update this as well. LR scheduler.step. So again, recap. What did I do? For every image, and these are clean images, I sample some random time step between 0 and 500. I go ahead and add that randomly sampled amount of noise, worth of noise, those many time steps worth of noise, to my images. And then I pass my noisy image and the number of time steps to my model, which predicts the noise. And my goal is for this neural network to be able to predict the amount of noise added. That's the noise pred. So the loss function is just a mean squared error, or Huber loss, or mean absolute error, between my noise prediction and the noise. Once we have all of that, we're basically kind of good to go, right? We have everything we need. We just need to do a little bit of plotting. So we're going to first do a progress bar dot update 1, so it's updated by 1, and then completed steps plus equals 1, because we've completed a full step of training here. And then the rest of this is not all that interesting, so I can just paste it in. This is just going to be using the every evaluation interval, right? So every once in a while, I'll go ahead and print out like how's the model doing, you know, that sort of stuff, and then go ahead and just make a plot using this plotting function we made up here. So let's go ahead and debug. Got an unexpected word. This should be a singular word, so scheduler optimizer. All right, got another unexpected keyword. Num training steps is, which one did I miss it on? Sampler. Oh, it was the, what did I call it in the sampler? In the sampler we called it the, oh, just num steps. Okay, yep, let's fix that. So this would be the DDPM sampler, num steps. All right, what else is wrong? Oh, yep, there's no rand and int, it's just rand int. Noisy images is not defined because that should be plural. All right, noisy inputs is not defined because this should be noisy images. Noisy, where was this? This is in our, oops. So this is in our original model, so that's up here. This should be noisy images. There we go. All right, what's up next? Time embeddings, not defined. Well, it's a misspelling. Time step embeddings, my bad. There we go. All right, so it's training. Again, watching a training loop is not all that interesting, but we can verify if things are working. Let's just, let's set the evaluation to like 10 steps. So every 10 steps, it's going to run the rest of the code. Looks like there's a bug. Noise coefficient times predicted noise. This is in our sampler. So let's go ahead and look at that. In our sampler, we have, let's see here. So our image predicted noise, I see. Okay, so the way, I think the problem here is that basically when I'm doing the inference here, right here, we want to make sure we predict the noise, but then we do .detach.cpu. Make sure this is not on the GPU at all. Okay, that didn't seem to help. Okay, yeah, that seemed to be the issue. So the issue was that basically I was taking it off the device, but then putting it back on the device for some reason. So we do not need you. So that can go. And then this scheduler is fine. And then we can let this run. I think it won't print anymore. Let's see. Oh. Okay, where am I printing stuff? Let's get rid of. Okay. And it looks like we're having NANs in our loss, so let's just do that. Print. Okay, so our loss looks fine. So what could be going wrong? Training. Print. Training losses. Oh, we're taking a mean of something we're not even storing anything in. So we need to do a quick training losses.append loss.item. There we go. All right, almost there. Tensor to image is not defined. Let's go ahead and fix that too. So this is tensor to image transform. So that's probably here. Make sure the rest of the code is working. Okay, looks like it's generating, and looks like there's still an error we have here. So no such file or, oh, that's fine. It was just trying to save something, and I don't have the folder built for it. That's fine. Let's just get rid of the save fig. Don't need that. Okay, saving. Nice. Okay, good. So obviously this is the very beginning of training, so it doesn't know any better. Hopefully it will improve over time as you train. But yeah, sorry about that. A couple of annoying bugs there. But yeah, okay, good. So again, let's just look at the final results as your model gets better. So this was plotted every, I believe, every 5,000 steps, and I trained it for 50,000. So you can see it starts to learn to generate reasonably okay faces, right? Obviously it's not the best, but this isn't a very big model either, and the data's not the best either. So this just gives you a general idea of the diffusion model. So let's do a little recap. So the main idea behind the diffusion model is, again, we have a noising process, and we noise it according to a specific scheduler. The scheduler is completely up to us, and I decided to do a simple linear scheduler, right? So right here, linear beta scheduler, which just linearly increases the variance of the noise we add at every step from 0.0001 to 0.02. The scheduler and the parameters of the scheduler are all hyperparameters that you can play with. And then another hyperparameter is how many steps of noise that you want to do. And so we can add noise, and then we train a neural network to denoise the image. Again, all of these formulas I covered in that very first video. So if you, again, you're curious to know where did all of these funky looking formulas come from, please go ahead and watch that video, because we hand derive everything, so you see where it's coming from. For the most part, the UNET is almost identical to any other UNET. The only new thing in the UNET that we have that we didn't have in our semantic segmentation is the inclusion of the temporal embeddings, right? We add some type of time embedding to our convolution. Specifically, we did it here in the residual block, so we add these time embeddings to the convolutions, and it gives the model an idea of, okay, I'm looking at this image, and it's been noised this number of times. That means I need to denoise it this much. And so it gives the model some context of how much noise has this image, how much noise has been added to this image. And other than that, this is a pretty standard implementation. I'm going to call it here because it's already a pretty long video, but I will see y'all in the next one.